Okay, welcome to Csaaw. We are pleased to be joined today by Bob Savit, who is in physics, and will be talking to us about something along the lines of statistical mechanics, complex systems, and agent-based modeling. And feel free to correct that if I've got it wrong. Thank you.
Okay, good.
But you're going to make 3 predictions, right?
No, I do not want to have a state as a problem.
Oh, okay.
That's highly problematic. Okay, so look, what I want to do is I want to. I'm in the physics department. I've been interested in statistical mechanics and nonlinear dynamics and complex systems for many years. What I want to do primarily is to describe to you, try to put in context, an interesting project that actually Rick and I are working on, along with a student who happens to be Rick's daughter. And then if there's, and I want to keep this as informal as possible, so please ask questions as I go along. And then if there's time at the end, we can talk in general about the question of statistical mechanics and why somebody who's interested in complex systems should be interested in statistical mechanics and should have some, why it would be helpful to have some background in statistical mechanics. So let me start, and Rick, please chime in if I'm missing something or you have some comments. So the project I want to describe to you is a project in co-adaptation or co-evolution. And when I say, so I don't have to keep repeating co-adaptation or co-evolution, I'll often use the word co-adaptation to subsume also ideas of co-evolution. So it starts from the following notion. If you have a complex adaptive system, there's, of course, they differ enormously one from the next, but you can identify some generic features that seem to be pretty common across various kinds of systems, whether they're biological systems or social systems, economic systems. And they're very broad, and they appear in different guises in these different systems, but we can name a few characteristics. For example, you have heterogeneous agents that act in different ways. You have, these agents are acting in some sort of environment which has some kind of structure to it sometimes. You have the emergence of, and when I say sometimes structure, I'm thinking of things like, for example, the formation of niches, certain pockets of the environment, areas of the environment that some agents can decide to exploit for their own benefit. When you almost always see in these complex adaptive systems some level of organization, and those organisms, those agents at some level of organization, cooperate or merge together to form organizations or structures at higher levels of organization. So you have single cells agglomerate together to form multi-celled organisms. You have artisans that come together to form factories, and you have bodies politic with various kinds of organizations, various kinds of hierarchies. You have companies that form together to form conglomerates, or form, in another sense, to form vertically integrated supply chains. There's all kinds of ways to use this approach. So the question, so since there are all these kinds of things, and all these kinds of, and there's also various kinds of interagent interactions. There's cooperative interactions, there's competitive interactions, symbiotic things, mutualism, all kinds of different interagent interactions. So the question is, where does all this stuff come from? And in particular, one question is, how far can you get in trying to describe the emergence of these kinds of features and these kinds of structures if you just start from the idea that there's co-adaptation, co-evolution in these systems? How much does the process of this sort of parallel adaptation result in what we observe in these complex systems in general? Now, if you think about co-adaptation, what you have is a bunch of agents, and again, they're heterogeneous, they're all different, right? And they're all kind of moving around, seeing the environment, seeing the actions of all the other agents, and they're all jockeying for position. They're all trying to increase some local utility function or amass some sort of wealth that they like to amass. And you think about it for a minute, you realize this gets to be a very complicated kind of interdependent set of behaviors that could create, I mean, could create nothing, but it could create something interesting. So, the project here is to try to start with models that are as, in some sense, as random or vanilla as possible, and have these underlying dynamics of co-adaptation. And I'm referring to them as meta-dynamics, because in a logical sense they're different than the dynamics that emerge between actors in this, in whatever system you're talking about. You can have cooperative interactions or competitive interactions between pairs of agents. The co-adaptation that underlies this isn't quite in the same logical category as those sorts of interactions. So we want to start off with a model that's as random as possible, but has co-adaptation in it, and see if we can see the emergence of anything that looks like the common sorts of structures that you see in various kinds of complex adaptive systems. Now, I'm a physicist. I'm a theoretical physicist. So, you know about the story about the dairy farm, right? Everybody knows this famous dairy farm story. Okay. I'll tell you this dairy farm story. This dairy farm decides it wants to increase milk production, and so it figures it's got to go out and hire the smartest person it can find. And of course, the smartest person it can find is a theoretical physicist. That goes without saying. So, finds a theoretical physicist, and it hires this theoretical physicist to consult on how to improve milk production. Gives him an office and a blackboard. The physicist says, "Okay, come back in a week, and I'll have an answer for you." So the chairman of the board, Corporate from Iowa, goes away, comes back a week later, and says, "Have you got the answer?" The physicist says, "I'm almost there. Give me till tomorrow." Goes away, comes back the next day. In the morning, he says, "Well, okay, you got the answer for us?" He said, "Just about. I'll tell you what, this afternoon, call a meeting with the board of directors, and I'll give you the result." This is great. So they call a meeting with the board of directors in the afternoon. They go into this oak-paneled room with a big fancy conference table. They're all sitting around, the board of directors of the dairy farm are sitting around there, and the theoretical physicist gets up and makes his presentation, and he says, "Consider a spherical cow." Now, the point of the story is that physicists like to simplify things as much as possible. And so this model that I'm going to show you is not a model of anything, or if you want to say it in other words, a model of everything. But that's what we do for a living. But the idea is that out of this, we might be able to get some sense of some of the nature of some of the underlying dynamics, or meta-dynamics, that can give rise to these kinds of things. So I couldn't get this PowerPoint thing. I'm kind of a Luddite. I couldn't get this PowerPoint thing to work right. So there's two subtitles to this. I expected, this is the biblical subtitle. Why doesn't the lion lie down with the lamb? So why is it that in certain kinds of circumstances you do have competitive interactions instead of cooperative interactions? What is the nature of those interactions that emerge? Or the more sort of teleological questions, do you get something, and by nothing varying random, some sort of randomness? Okay, so let me describe the game to you now that is going to be the basis for these models. So this game has n agents, and I gave this talk yesterday, and so I got something that I wrote, erased them. So this is a game that has basically three parameters. It has n agents, and the agents act on an environment. And the environment can be in any one of E states. Now, ab initio, this game does not include agents interacting with each other. They interact with each other, as it will turn out, only through the medium of the environment. So this is a stigmergic process. And I know all of you have better reading than I do, so you all know what stigmergy means. That it's information transferred through the medium of the environment. So they're N agents, and they act on the environment.
How does this differ from a network where the agents are nodes and the environment is...
Listen. So you have N agents, and the environment can be in any one of these states. And what happens when it's an agent's turn to act? The agent looks at his local environment. Let's say it's in state E1. And the agent acts according to the strategy that he's using. And the strategy tells him what to do. The strategy says, okay, you see environment E1, it's your turn to act. You change environment E1 into environment E2. And as a result of changing environment E1 into environment E2, state E2, you get a payoff. And this strategy also includes the value of the payoff for that action. The payoff can be positive, negative, or 0. And so to make things simple, the payoffs have 3 values in this simple version of the game: +1, -1, and 0. And then after that, the strategy also includes a move order. So the agent does what he does to the environment, gets his payoff, and then moves to the left or the right or up or down, or wherever he's moving, depending on how big the space is that you're working in. So a strategy that an agent uses is a lookup table that looks like this. So in the first column, this is a lookup table for 7 states. The first column is a list of all the states in order. The second column is the list of what state this, if the agent sees environment 4, for instance, this strategy says turn it into state 7. And if you do that, the third column says you get a payoff of +1. And then after you do that, you stay where you are. And then it's the next agent's turn to act. Now, the important thing about these lists are, except for the first one, which is the list in order, all these other lists are random in the following sense. This list is going to be a list of the E states, an IID list of the E states. So you imagine that you have an urn with E balls and different numbers on them. You pull out one, you write it down, you put it back in, you mix it up, and you write it down. Okay, so this is an IID, independent and identically distributed list. This is a random list of 1s, -1s, and 0s, but with the additional constraint that the sum has to add up to 0. So all these strategies are revenue neutral. And then this is a random list of what direction you go. Yeah.
Just checking this, it looks like the payoff is a result of the transition, not the state. So
It's a result of the transition.
So you're paid based on what the state was originally.
Yes. And then you change the state. And then the next guy who sits on that site, sits in that area, sees that new state that you changed it to. Now.
Bob, I'm sorry, but one other thing I'm not quite clear on. So I'm in state 1. Is the random assignment once for all, or meaning that 5 always follows 1, or it follows 1 at random?
No. So let me. Okay. If what I say now doesn't clarify, ask the question. Okay. So this is a strategy, and that one of the agents could be using. But the agents are now. If each agent had one randomly generated strategy like this, then they'd always have to use that strategy, and it would be completely algorithmic. There's not very interesting. But the agents have S strategies each. So each agent has a set of strategies, S some number bigger than 1, and each of the agent's S strategies is a different a priori, different random list, right? And then the agent is adaptive in the following sense. The agent, at a certain point in the game, when it's an agent's turn to act, he has to decide which strategy he's going to use to make his decision, right? So, in the simplest way of doing this, what he does is the following. He says, okay, I have these S strategies. Which strategy would have given me the most points had I used it for all times in the past up to that point in the game, right? So there's a counter associated with each strategy, and it says, well, if I used it, then what would I have gotten, right? And he uses the strategy that would have done the best at that point, up to that point in the game. Now, if later in the game another strategy accumulates more virtual points, then he'll change his strategy. So it's adaptive in that the the strategies that the agent is using can change, but it's not evolutionary in the sense that the strategies are fixed once you have them. But they're all different in general for all the different agents. Does that answer your question?
Yeah.
So there's no restriction on like if I define like 7 strategies, for example, then I could use strategy 1 and then the next move strategy 2 and then there's no...
If strategy 2 happens to rise to the top of the pile, then you can use it. So now there are other ways to do this. There are variations on it. I don't think it makes much difference. You could do it you could choose your strategy probabilistically depending on the weight that it has. You could look at points accumulated at a discounted rate, so you ignore the ones that are in the very distant past. That doesn't seem to make a few runs we've done. That doesn't seem to make a difference.
Just to follow Gene's question, then the strategy I use next is the one, so to speak, at the top of the pile.
Right.
So
Yeah, whichever one is at the top of the pile at the moment that you're supposed to act, that's the one you use. Yeah.
Are moves of the payoffs associated with moves from states consistent around over rounds? So if in round 1 I move from 5 to 6, is that going to yield the same payoff as if I move from 5 to 6 in round K?
It depends on which strategy you're using. If you're using the same strategy, then you get the same payoff for the same transition. But another strategy of yours may turn out to be better 10,000 time steps later, and you're going to use that instead.
yeah, but isn't this
Strategy is not the
Abe's
move.
question?
What?
Strategy is everything on that table except the first column.
Right.
Yeah, but Abe, did you make the point that the payoff depends on what your current state is?
The payoff depends on what environmental. Okay, given a strategy, the payoff depends on what environmental state the agent sees at the moment that he's supposed to act.
So these agents are not strategic in a game theoretic sense. They're looking at several possible strategy profiles they could choose from, looking at their current right? Because if that were the case, if I'm sitting on a 4 space, then I'd say, great, this strategy pays off for me, let's use that one. But if I'm sitting on a 7 space, I say, oh, let's pick a different profile.
No, yeah, the strategy. Okay, a strategy is a list of everything that you will do under all possible circumstances that you're going to face. It's not just what you're going to do at that moment. Right? The strategy contains all the information that gives you a response.
But what I'm saying is
Yeah,
the choice of the strategy is
there's
dependent on
payoffs.
past payoffs.
Right.
It's not dependent on your immediate circumstance. Because if it were dependent on your immediate circumstance, you'd always just pick something that gives you a payoff for sitting on a type of resource.
You can't use a strategy at the bottom of your pile, even though for that particular state it would have been better.
Okay.
Is the intuition behind this that there might be a set of fixed physical laws and an agent is searching, say, for the path of least resistance?
Well, the intuition is more like, okay, this is what I've done before that seems to be working pretty well, and I'm going to keep doing it until I have a reason to change. Okay, should I go on? Okay. So this is the game. So the idea is you start off with some substrate, 2 dimensions, 3 dimensions, 1 dimension. You start off with a bunch of agents, and you let them go, and they take turns. Now, I didn't specify the order in which the agents take their turns. So most of what I'm going to talk about are games in which the agents act in random order. I'm going to also show some graphs for what happens when agents act in a specific predetermined order. But I'm showing you that qualitatively, at the level we're talking about now, it doesn't matter. I'm showing you a couple of graphs for the fixed order games because they look pretty. But just take my word for it. At the level that we're talking about, you get the same features in either case. Okay, so we have first started off doing this with a one-dimensional world. So we have strategies like this. But we found out it was too complicated. So we went to a zero-dimensional world. So all the agents are sitting at the same site. And so the move column here is the strategy is absent. And they just take random turns altering the environment. And they play their strategies and they choose their strategies according to that. So what do you get? Okay, there's a lot of different things you can look at, and I'm going to just tell you about a couple of the broadest metrics, but there's a lot more to this, and a lot of really interesting detail, even in the zero-dimensional game. So what I'm going to show you are a couple of graphs. They are going to be plots of different results of different games played with different values of n, number of agents, different values of environmental states, and they're going to be color dots here. So I'm going to first show you one which is the average wealth accumulated by the agents, or the rate of wealth accumulation by the agents over the run of the game. And each game was played, for each value of E and N, we had something like 20 different games that we played, and so I'm showing you is the average over all these runs. Okay, everybody understand? So this actually is from the fixed order game, but like I say, it's prettier. The random order game is roughly the same. Now this is the color scale. The light colors mean a lot of wealth is accumulated. Actually, the top here is 1 point per turn, which is the maximum you can possibly do. Right, and then it goes down to nothing down here. If you look at it for a minute, you can identify roughly 3 regions in this graph. There's a region where they're doing extremely well at gaining points. Remember again, all the strategies are revenue neutral, right? So a priori they shouldn't be doing anything. So there's this region which has a sort of hyperbolic curve here, and in this region they're doing extremely well. This region they're also getting some points, right, down here, but less so than over here. And there's a fairly rapid fall off from this region to this region.
Sorry, what's the axis?
This is the number of environmental states. This is 70, E equals 70. This is the number of agents, also 70. And if you squint, you can see down here at the bottom, there's a kind of a wedge that runs up like this. It's not so apparent here, but there is a wedge here where they don't earn hardly anything. They do lousy. Really, really lousy. So, roughly speaking, what you have here is a wedge called region C. You have this larger region B, and then you have this curve that looks sort of hyperbolic, and that is region A. So here they're doing great. Here they're doing okay, and here they're doing lousy. Now I'll tell you, if you let each agent have just one strategy, so they're not adaptive, then they always do pretty lousy. They're pretty close to 0, which is what you would expect. Okay, so why is it that they're doing as well as they are? Here, let's on the next slide. Let's see if it helps. Yes. Okay. All right. Now, if you think about it for a while, if I shouldn't have showed this. It's more startling if I gave you the story. Think about it for a while. Since all these strategies are revenue neutral, right? Think about the probability after this game is played for. Think about the probability that different environmental states occur, that the frequency of those states occur. Now, a priori, you would expect that since everything's random, that the probability for each state occurring is the same. It should be 1 over capital E, where E is the number of states. And if that were true, if all the states occurred with the same probability, then you would be guaranteed that the agents would all earn exactly 0 points, right? Because that's what their strategies tell them. So if they're earning positive points, it must be that somehow the environment is being skewed in some way. Now, how could that happen? Well, you can imagine it could happen in the following way. Let me go back to the previous slide. I've got to put on this. Okay, I want this slide.
A quick clarifying question.
Yeah, sure.
The bottom axis, the x-axis there, is that the number of agents or the number of strategies per agent?
The number of agents. Oh, I'm sorry. In that picture that I showed, each agent had S strategies. S, I think, for that was either 64 or 100 agents.
Okay.
So each agent had. completely numbered strategies.
And you run it randomly. So you have like for each stage, you just run it like for how many times?
How long are the runs? Long. And actually, that data is calculated taken from the end of the runs. I mean, the runs are 2 million
Are
times.
you doing it randomly, or are you doing it so that like the agent learn that like so you do like run it for a while and then like the agent learn something out of it and then you like learn more like that, or are you just like
No, it's just what I said before. You start off the game, you run it for your 5 million time steps, whatever you're going to do, and the agents are always accumulate their strategies, are always accumulating points, and they're just playing the game. And then you look near the end, let's say, the last 100,000 time steps to collect your data about wealth accumulation. Okay.
If you run them in a fixed order, then once you've started the game, there's no probability distribution. It's deterministic at that point. If you run the agents,
Except that you get regime changes. You do get regime, and it's actually quite brittle. Because if one guy decides to change his strategy, because everybody's fixed in lockstep, that really screws up everybody else's calculation.
But the determination to change the strategy that you described first was the deterministic, just based on what the previous payoffs would have been and stuff like that.
Yeah, no, you can think of that. This is all deterministic in that sense.
Yeah, in that sense. Yeah, no, I'm not saying that you don't get interesting
right. I
results.
thought you meant that. No. The question of action, if we have time, I'll talk about that a little bit. The question of whether the agents fix on a strategy and stay with a certain strategy, or whether they continue to flip their strategies is a very important question.
There's a little bit of stochasticity in what do you do with ties.
Yeah, I was wondering about that, whether you just did a linear ordering or whether you flipped a coin for ties.
Or even flipping your coin for ties.
Yeah, okay, so there is some. Okay, cool.
Okay, so how could it be that you can get a distribution of states, probability distribution of different variable states that isn't flat? Well, for example, remember that second column is an IID column, but because it's an IID list, you can have the same state appear more than once. So let's suppose that there is some agent out there that likes that when he sees state 7, he gets a reward, right? Now this agent, you see, has 2 7s in his output column, right? So he's more likely to produce a 7 after he acts than another state. If that agent who likes to eat 7s follows this agent, then that's going to be good. Now, if that agent who likes to eat 7s has, let's say, 2 insertions of 4 in his second column, then this guy likes 4s. This guy gets a 1 whenever he sees a 4. So when he follows the other guy who likes 7s, right, then he's more likely to see a 4, and so this guy will like 4s, and of course he's going to produce more 7s. So one of the guys is producing 7s, the other guy eats the 7s and produces 4s. The 4s, this guy eats the 4s and produces the 7s, and you can have sort of mutualistic behavior. Great, but then you think about it. The problem with that argument is that since these agents act in random order, the probability that you have one agent following the other agent is only 1 over n, right? So you think, well, that's not going to happen very often. But there are combinatorically many ways in which you can have these strategies. You can find self-reinforcing behaviors. So it may be that this may be the case, and there can be other combinations of behaviors also that produce other kinds of, we call them niches, in the sense that those environmental states occur more often. And so you're simultaneously producing niches and producing the agents to exploit those niches. Okay, so let's see. Saw that. Okay, so here is an example. This is for gameplay. This is for random order agents. This is a gameplay with n equal 10 agents and 10 environmental states, and these are the histograms averaged over. I guess let's see. 10,000 time steps. 3 successive 10,000 time step windows. And you see that in this histogram there are huge deviations. The gray stuff, the brown stuff, whatever it is what you would expect if everything was completely flat and random, right? So you see there are huge variations in this histogram. And even more interesting is that it persists. I mean, they're not identical, but the major deviations persist over these time steps. So you do that, get this kind of self-reinforcing thing. Now, you might suppose that the wealth produced by an agent is somehow, or average wealth produced by agents is somehow correlated to the environmental, to some measure of the environmental order produced. And you would be right, more or less. So to measure that, to measure the environmental order, we can produce, first we calculate the entropy associated with this distribution. And the entropy, for those of you who don't know it, is just, here, we sum over all the environmental states. This goes from 1 to capital B, of the probability that that state occurs, times the log of the probability that state occurs. If you're not familiar with this form, don't worry about it, but this is a very commonly used form for measuring disorder. So the larger this number is, the more disorder there is, in the sense that the more uniform the distribution is. The flat distribution with all states occurring at the same rate is the most, quote, disordered, end quote, state. Now, when I first learned about this, it seemed to me that was, why is this, it seemed to me that was the most ordered state. Right? It's simple, right? That's a whole other story. But just, just accept the nomenclature for the moment. So this is the most disordered state if this is big. If this is small, then it's the most ordered state, and the most ordered state you can have is where the probability is 1 for one state and 0 for all the other states. And then from that, we can produce a quantity called the environmental order, which is just 1 plus 1 over log capital E times the entropy. And this has the property, you can finish stuff later, this has the property that when the entropy is maximum, this is 0. When the entropy, and when the entropy is minimum, this is 1. So it normalizes between 0 and 1. You have a question?
I was just going to use the word normalizes.
Yeah. Okay. All right. So this graph is this is the entropy, not the order. This is one run. Again, the agent's acting in random order. But what the entropy looks like as a function of time. And this gray bar is what you would, the two standard deviations of what you would expect if you just had this sort of histogram random fluctuations on the glasses.
So if you ran it with s equals 1, right?
No, not actually. It's not exactly s equals 1. It's close. It's that actually was calculated with the random, not with s equals 1. With just the random distribution with some fluctuations. Okay, but it doesn't matter. That's a detail we don't have to worry about for now. But you see, when the game starts off, the entropy is very close to what you would expect randomly, which is right, because the agents haven't learned anything about each other. And then it falls, and then there's fluctuations, but it's very significantly below what you would expect just from the random distribution. So these agents co-adapting and watching what each other are doing through the medium of the environment are producing something like niches, some kind of structure. Here is the same kind of graph, which looks sort of familiar, but I showed you before for the mean wealth for the agents. But this is actually that measure, this measure of environmental order. And you see, more or less, it's got the same three regions. It's got this region here where the environmental order is very high, where the agents do extremely well. Then it tapers off, and it's also got this wedge down here. Okay. Yeah.
So I can't see the numbers there. Are the axes the same?
The axes are the same. Yeah.
So the slope on that wedge looks like it's basically linear, but increasing at less than 1.
Right.
Which means that as long as the number of strategies goes up past the number of agents.
No, this is the environmental states.
I'm sorry, the number of states goes up past the number of agents. People can be kind of reasonably happy.
Yeah.
Is this where you're going? Sorry.
Well, I'm going to say something about that. That's a good observation and question. So I'll come back to that in a minute. I may come back to it right now because I course on the next slide. Okay, this is, well, forget, let's skip this. Okay, before I show you this flippant book, let me go back and fix this. Okay, so we have these, roughly speaking, these three regions here, with these separatrices. Now, it turns out that the nature of this separatrix from A to B is qualitatively different than the nature of the separatrix from C into A or into B. Okay, so let's first ask the question: why are you getting such high environmental order here and such good wealth here and not here, with a very rapid fall? It was puzzling for a long time. But it turns out you can do a little back of the envelope calculation. You can. This is already like a spherical cow model, right? But you can make it even. I don't know. It's more spherical than you can make it even more simple.
Point.
Point. Okay. Right. The point model. So we can ask the following question. Let's suppose we had n agents and e environmental states, and each agent had s strategies. Okay. And let's try to calculate the following probability. What we want to do is we want to calculate the probability that with these strategies being random, that we can find a set of strategies among all the agents, one strategy for each agent, such that only a subset K of the environmental states E, the total environmental states E, are visited by that list of strategies, and each agent gets a point plus one. Right? Everybody understand the question? Right? So let's fix K. Say K is 2. What is the probability that I can find, if I have S strategies, random strategies for N agents and E environmental states, what is the probability that I can find a solution where I visit only 2 states, and each agent, when it visits one of those 2 states, always gets a reward of plus 1. So it turns out that you can do that calculation, and the region where the probability is very high is actually has this sort of same hyperbolic shape. So the idea is that in this region, this is where the solutions, where you can have a fairly high probability of finding a really good solution. I mean, that's a cartoon. Cartoon already of a cartoon. That's a line drawing of a cartoon or something. So, but in this region, you have a very high probability of there being such a solution, and somehow this adaptive, co-adaptive system is finding some solution like that. I mean, not exactly that solution, of course, because you saw that it's not that a bunch of the states are empty and only 1 or 2 are visited, but there's a lot of variation in what gets visited and what doesn't get visited. And then over here, that solution, the probability of that solution existing falls off very rapidly. Right? It falls off very rapidly. It's not a bona fide phase transition, but it does fall very rapidly. And you might anticipate that as you raise the number of strategies, that this curve will move out. And if you have a very large number of strategies, maybe we'll subsume this whole region. And in fact, a proxy for that, now we haven't done this calculation, that's something that is really interesting to do. A proxy for many strategies might be evolution of the strategies themselves. So it could be the case that if you do evolution, it could be the case that something entirely different happens. But it could be the case that if you do evolution, you get this region B largely disappearing, and you have a much richer behavior, much more behavior in which the agents accumulate wealth much more over a much wider region. Okay, that's that. Now, what about this other separatrix from region C to region B? If you look at the behavior of the agents, what I'm going to tell you now isn't exactly right, but it's close enough probably. If you look at the behavior of the agents in terms of their strategy choices, what you find is that in regions A and B, most agents in a game tend to fix on a strategy and stick with it for a very long period of time after you play the game for a while. But in this region C, that's not the case. In this region C, agents are always flipping their strategies. extremely rarely find agents that don't change their strategies every time step observed. So, not qualitatively, well, if that's what they're doing, then that's going to screw up the environmental order thing. You would expect that that's going to create a histogram of the environmental states that's more flat, which indeed is the case. And you might also expect, and because of that, and because all these strategies are revenue neutral, they're not going to gain much wealth, and that's true too. Now, it turns out that this transition from C to B is a bona fide phase transition, as you have in statistical physics, which is a nice segue to part of the system mechanics. It's a bona fide phase transition. In an infinitely large system, there will be, at this point, a real singularity, discontinuity of some kind. You can choose as an order parameter, as something that sort of tells you something about the nature of the phase that you're in. You can choose something related to the way in which the strategies are flipping. Here, they flip a lot, so the order parameter is small. Here, they don't flip hardly at all, so the order parameter is large, and you can have some singularity here. Okay, so far so good. But, in fact, it's more interesting than that. We believe that this phase transition isn't just a standard phase transition like you see in, let's say, magnets. You have these models of, you have ferromagnetism. Right, if you take a piece of metal, magnetic, something that's magnetized at a room temperature, let's say, so it acts like a magnet. What does that mean? That means that all the little spins, all the little electrons that are running around the little atoms in there are kind of all running around in the same direction, so it creates a magnetic field and a non-zero magnetic moment and acts like a magnet. If you heat that up, then you can heat it up so that the thermal energy is, thermal wigglings of the electron orbitals are high, and you can get some of them to flip over, and finally you get a region where it's paramagnetic, where the thing is no more magnetized. And there is a phase transition from the ferromagnetic phase, where all the spins are kind of pointing in the same direction, to where they're kind of wiggling around a lot, and there's no magnetism. That's the standard phase transition in statistical mechanics. But there's another kind of phase transition, which is much more subtle and much more confusing, and it's called a replica symmetry breaking transition. Now, so let me tell you what this is relevant to. The model that the situation I described to you about the magnet is a situation in which you have an ordered system, right? All the little magnetic moments are pointing in the same direction, and it goes into a disordered system. But the interaction between all the little magnetic moments is all the same. So in a ferromagnet, if one spin is pointing up like this, the orbitals are like that. The one next to it, the interaction is a ferromagnetic interaction. The one next to it wants to be pointing in the same direction too. There are some systems where that's not the case, where you don't have all the interaction of all the constituent parts the same. An example of that is window glass. Window glass is an amorphous material, and the interactions between the elements of the window glass are not all the same. In terms of a simple model, some of the interactions would want the, if you thought of the window glass somehow as having to do with spin orientation, some of the interactions would like the nearest neighbor spins to be pointing in the same direction. Some of them would like them to be pointing in the opposite direction. Turns out that disorder, that amorphousness or fixed disorder in terms of the interactions, makes an enormous difference in the way the system behaves. And it was really, it's okay, you told me before you had to go. It makes an enormous difference in the way these kinds of systems behave. It was, for a long time, it was not clear how you describe these things thermodynamically or in terms of statistical mechanics. In the 80s, late 70s, 80s, largely the work of an Italian physicist named Giorgio Parisi, who's a brilliant guy, invented a formalism for describing these systems, these amorphous systems. And the formalism was called the replica trick. Now I'll tell you, mathematically, it's very confusing. It makes no sense, really no sense. And people still argue about whether it's right or not. but it works, and it's really cool. And this transition here, and it exhibits a different kind of transition than the ferromagnetic transition that I just described. We don't have to go into the details now, but it's much more complicated, much more interesting. And we believe this transition is of that nature. Now, what is it about this system that, in order for the transition to have this disordered feature, this replica symmetry breaking feature, there has to be some sort of disorder in the system. What is it about this model that's the analog of the disorder in glasses? The thing that carries the disorder in this model is the fact that the agents are heterogeneous. That really, if you trace through the formalism, that is the analog built-in, what physicists call quenched disorder. That is, it's a disorder that's fixed for the whole run of the game. What's fixed for the whole run of the game in terms of disorder here is the fact that these strategies are all fixed. Right? So, okay. So anyway, the point of this little digression is that this replica symmetry breaking formalism may be really important to describing lots of different adaptive systems in which you have heterogeneous agents interacting.
Bob. So
yeah.
what do you think is going to happen when we turn evolution on?
I don't know. That's why it's so interesting. I don't know. It could change the nature of this transition. Okay. I think. Oh, let me show you the flip it, and then I'll be. Okay, so these agents, from the beginning, these agents didn't interact directly with each other, only through the environment. However, if Agent A acts, and he produces an environmental state, and Agent B acts after Agent A, then whether B gets a reward or not depends on what the state is that Agent A has produced. So you can think of, over the period or long window of the game, you can think of representing this as an induced interaction of between Agent A and Agent B. If Agent B follows Agent A, is Agent A giving B goodies, or is he punishing him? And then vice versa. If Agent A follows Agent B, right? So you can construct a kind of network in which you have all the agents as nodes on the network, and pairs of lines between the agents with an arrow. So one going to one agent, one going to the other agent, and you can carry the information about whether one agent is benefiting by the other agent's actions or not. And let me show you what this looks like. And this is just going to be. I'll tell you right now that I have two flipped books here, one for 6 agents and one for 9 agents. Let me do the 6 agent one first. We haven't analyzed this, so I don't know what this means. You can kind of get a few ideas by looking at it. Now the blue, okay, so the more intense the color, the greater the benefit or the harm. So very intense blues mean great benefit. So here's an intense blue line. So 3 benefits whenever he follows 2. Not whenever. The red ones, the color doesn't come out for. Okay. The red ones means harm. So right. And this is average, I think, over 10. These are the sequence over 10,000 time steps. So let me just flip through it quickly. It looks better on this. So you see something. One thing you see is that you have this little parallel pipe in here. That seems to persist for a while. So there's something going on there that's a mutual benefit. But other things are wiggling around. We haven't had a chance to analyze these things or what they mean, but I think there's something interesting here about more details about the way in which this co-adaptation works to produce the order that we see in the environment.
And presumably those are things like parasitism, mutualism, competition, that sort of thing.
Right. You can
depending on the relationship with the numbers.
Right. At least in an analogical sense, right? But they're all induced through the environment.
I'm sorry, I'm gonna ask this to
There are no stupid questions. There are only stupid people. But I'm sure you
Well, there are also stupid answers.
I'm sure you have. You will give a stupid answer.
So, how do you measure color again? So that's like one time, like one six, like
Each one of these pictures is averaged over 10,000 time steps.
Oh.
It's the result of
Okay.
what you get.
Okay, that makes so much more sense than
Okay.
one.
Right.
Yeah.
So, just for fun, I'll show you what it looks like with 9 agents.
Does it accumulate though? No.
What do you
So it's
what?
just like that 10,000 times, but it doesn't accumulate.
No, each picture is just a 10,000 time step window.
That's a sequence of 10,000 step averages.
Right.
So no, I mean, there's this average, so the next average is independent, not cumulative,
Okay.
Right.
at least as I understand.
Yeah, that's right. Okay, here's 9 agents. Those are the specs. So you can see if you see anything. If you see anything startling, let me know quick. You can publish it. I mean, it's true as you would expect that as time goes by, you get more blue lines and red lines, which is what you want.
So one of the kinds.
There's a measure of red lines.
Yeah, there's
So, so one of the kinds of things we'd like to do is understand when do we get more blue lines and red lines, or when do we get more triangles of
Right.
whatever.
One thing I did notice is you had that parallel pipe at that first side figure that was sort of like this.
Right.
And then later you got a bigger figure with more lines. That, if you could show that that was a trend, that would be very
Right,
interesting.
right.
Yeah, I think that's right. What's the probability distribution of clusters of mutual reinforcement, for example?
So one thing that you mentioned earlier that I haven't seen you come back to so far is organization into hierarchies.
Well, maybe you can. I'm not pushing this too hard, but maybe you consider if you have a long time period where you have these guys that are mutually reinforcing, maybe that's a prototype of an organization to a hierarchy structure.
So I was actually thinking of exactly the opposite thing there. So coming at this from a political science perspective, in game theory, people talk about the price of anarchy. So if you have different agents who are dueling back and forth and essentially they harm each other, so people in a red network, they would say, but it's possible that those, let's say there are 3 agents who are in a network where they're all hurting each other, and they do it pretty regularly. You could imagine that, yeah, you can think of bad relationships and things here. You could imagine that it might be worthwhile for those 3 agents to get together and come up with some kind of binding contract where they say, look, I'm not going to do the thing that hurts you anymore if you'll stop doing the thing that hurts me. Right? So in the language of this, if they have a strategy profile that's mutually reinforcing in a good way, or at least as not as harmful as the other one, then some kind of government would be helpful for them. And that might actually be the place. So for agents who get along pretty well already, who don't harm each other, who are able to support each other in a cyclic way, they don't need government because they're already pretty happy. But agents who hurt each other in a systematic way would actually have the biggest incentive to tie that. In the language of this, what you'd say is they're no longer allowed to play certain strategy profiles.
Well, so okay, I think I see what you mean. But this reminds me of another point, actually, that I was going to mention at the beginning. There's a certain, if you think about this in the game theoretic context, but let's suppose you think about it in the game theoretic context, there's a certain sense in which this is in the same spirit as a couple of papers that I think appeared in the last year or two. One by Sci-Levin at Princeton and one by Roughgarden at Stanford. And those are games, they're playing a game in which not only do the agent's strategies evolve during the game, but the rules, the payoff agents evolve. So the nature of the game evolves also. This is sort of in the same, I mean, it's a very different structure and language, right? But it's sort of in the same spirit of those things.
Yeah, I'm not familiar with those papers, but that sounds right to me.
Along the lines that you're talking about, Abe, it would be interesting if you set this up so that there could be 2 self-reinforcing domains but with some kind of interference across them, so that you would get both the government effect. We're going to agree not to do but we're still going to keep our coalitions, kind of thing. If that emerged, that would be, and both Roughgarden and Levin would find this kind of thing very interesting. Yeah, that's interesting. One thing, to go back almost to the beginning, you said that this notion of if all the states are equally likely, that seems highly ordered. And of course, this is one of the main.
You mean the real term is
intuitively that seems.
Right.
Yeah, and this of course has been a big argument against entropy stated that way, because it doesn't involve, if I go through all the states, but every state predicts the next one exactly, it still has the same entropy. So one suggestion here, what changes that a lot is if you use conditional probabilities.
Yes.
And do this, because then you capture this kind of conditional order that simply gets wiped out if you do ordinary entropy calculation.
There's another very interesting, another way to confuse yourself, very, very interesting way. In statistical mechanics, there's a phenomenon called duality. And and duality can be applied to lots of different models. Primarily, it works really well in abelian models. But one of the models that and the place it was first noticed was in the two-dimensional Ising model. Now, the Ising model, who knows what the Ising model is? All right, the Ising model.
That's what you do to cakes, right?
Yeah. So, Ising model.
Yeah.
That guy, Ising. The Ising model is a model in which you have. Let me just stop. So the two-dimensional Ising model on a square lattice. You have a lattice, and at each side of the lattice you put a spin, an arrow. The arrow can point out of the border into the border, up or down. And there's an interaction between nearest neighbor spins, so that the energy of the interaction between nearest neighbor spins is some constant J times SI, SJ, where SI and SJ are nearest neighbors. And the total energy of the whole system is just the sum over nearest neighbor pairs. That turns out to be the total energy of the whole system for the Ising model. And for the ferromagnetic Ising model, J is positive, J is negative, so that the system lowers its energy when the spins point in the same direction. Ground state energy. Right? Okay, and then you can do statistical mechanics on this and all that kind of nice stuff. And what you find is that at very low temperatures, there's a temperature, also take this thing and you think of the temperature, there's a temperature, right? At very low temperatures, the state that's preferred is all the spins pointing in the same direction. As you raise the temperature, you come to a critical point where there's a phase transition, and suddenly you go from a state in which what's preferred is all the spins pointing in the same direction to this preferred state being the spins pointing in opposite directions. Not opposite directions, but randomly oriented, right? So what you would say, classically, is that the situation in which all the spins are pointing in the same direction is a state of low entropy, right? Because it's very ordered. All the spins are pointing in the same direction, right? Whereas the high temperature state is a state of high entropy. You don't know what it's going to look like. You got all kinds of random possibilities for the orientation of spins, okay? Low entropy at low temperatures, high entropy at high temperatures. Everybody's happy, go home. However, there is a transformation that you can apply to this model called the duality transformation. And it turns out when you apply it to this two-dimensional Ising model, the duality transformation maps the two-dimensional Ising model into another model, which happens to be also a two-dimensional Ising model. It's the same model, but with a different parameter in front. And it turns out that the parameter for the dual model, the two-dimensional Ising model, is such that the temperature is inverted. So in terms of the original description of the Ising model, high temperatures is high entropy, low temperatures is low entropy. But in terms of the dual description, high temperatures is low entropy, and low temperatures is high entropy. The whole thing just stands on its head. There are these are order parameters, right, which have low entropy at low temperatures, high entropy at high temperatures. In the dual model, you can identify something called a disorder parameter, which plays exactly the same formal role that the order parameter plays here, but in terms of the entropy, it's completely reversed. And that's kind of consistent with, when you first hear about what's order, what's disorder, your intuition that something's screwy about these words that are being used. Right? But there is a certain sense in which a flat distribution actually is extremely ordered if you look at it in the right set of variables.
So, were you thinking of your government as being something added on top of the model, or were you more thinking of the government the way I think John was suggesting, sort of government emergence, in the sense of one coalition sort of controls the other?
I was going in the other sense, saying that this is a model of people who are, or people or whatever species that are acting independently, and when you take kind of the Hobbesian view of government, it's an outside force that acts on people that changes their available strategies, and when things work out nicely, makes them better off.
It's possible, I think maybe this was John was suggesting, I think it's possible to imagine some subset of these guys getting organized and having links over to the other subset, so that the one subset organizes, puts the pressure on to organize the other subset.
Yeah, that's what I thought was at least feasible.
Yeah.
That would be fair.
I agree with you.
So if you could find some type of initial shape that leads to the formation.
Yeah.
So there are a lot of things to do with this. This is not just the spherical problem in 0 dimensions. We want to see what happens with an evolution. We want to see what happens when we include spatial degrees of freedom. So don't just look at what were the other? Well, we want to really like to analyze these graphs that come out to see what kinds of things are going on. What that tells us about how this occurs. And there's several other. Oh, another big area is to try to talk to people who are really have significant domain knowledge in different areas. Like, is there a way in which you can understand, which you can make connections with these very broad models to real ecological systems, for instance, so that you can try to look for some of those. Right? Is there something like a space transition as a function of, I don't know what parameter, ecological system? That would be good.
This reminds me of the subsection, I guess, combinatorics of Ramsey theory. Are you familiar with these ideas? It's in mathematics, but it's the idea in a network, if there are certain vertices, certain nodes, its order will always occur relative to what distribution is initially begun in. So perhaps there's some interesting analog. I know if we have, say, certain numbers of nodes and vertices, then no matter what distribution, what random distribution one will start in, there must be, say, X amounts of triangles or whatnot. So perhaps there's some analogy between the triangles, the shapes that are appearing here, and also the relationships that would occur. I know there's a lot of outstanding problems in that field too.
Ramsey theory is actually not a bad idea. This is the idea that if you have a long sequence of random numbers, that it tells you how many 1, 2, 3, 4s are you likely to find as a proportion of the total.
Right.
Stuff like that. I mean, that's the simple version. But yeah, Ramsey really did some interesting stuff.
Also, I'm curious, how would you handle these things analytically? Is it just totally intractable, or?
It's not totally intractable. So
This is the creative use of not in English. It's not irreparable.
right. You're not entirely wrong.
Yeah.
Well, you can. Depends what you mean by analysis. I mean, you can make cartoons of this, like when this calculation about the probability of finding a subset K of states that are visited. Right?
So I guess.
But you can map, as I alluded to earlier, you can map this model analytically. You can map this model onto a spin glass model. So you can use some of the techniques there, which are sort of a little bit analytic. little bit numerical to try to get more insight into what's going on. And we know how to do that, how to map it onto the spin glass. So there's something that you can grow. There's another model. Actually, it's very different, but it has some of the same features, and it's in a much simpler context, which is called the minority game. And the minority game actually has the same kind of transition that we see here, that we think we see here, this replica symmetry rate transition. And in the minority game, you have the same. The controlling parameter is quite analogous. You have signals. Basically, the controlling parameter here is the number of signals divided by the number of agents, right? E is the number of environmental states. You can think of that as the number of signals, the different signals that an agent can see. In the minority game, there is a phase transition when this ratio, when the analog E over N, the number of signals divided by the number of agents, is also equal to a constant. Interestingly, the value of that ratio in the minority game is not so different than what we seem to see for the slope of this line. And I don't know if it turns out it's like a zero of a zeta function. It's some irrational number. I don't know if it's the same number. It would be just remarkable if it's not the same. But it's the same ballpark anyway. It's about a quarter of a second.
I think it might be worth looking for too. Is if you keep the ratio of strategies to agents constant and move up the number of agents.
Strategies to?
So you have more and more agents.
Yeah.
I wonder if that dotted line would become sharper and sharper. So the dotted transition, whether that would have become ever more and more like a real transition.
As you increase strategies.
Yeah, just
Strategies.
Yeah, I did say it.
Say it again.
Both. I mean,
strategies increase presumably.
Yeah, I thought I didn't see a simple way to do that. I thought about that actually. Whether there's a thermodynamic limit. Is there a thermodynamic limit for this?
Yeah.
For this
Exactly.
curve? I didn't quite see how that would work out.
Yeah.
So it'd be cool if there was.
Well, it's become this key result of computer science that these NP-hard problems, as you get more and more, as the size of the problem, the number of nodes goes up, where the transition gets sharper and sharper.
Right.
And that's had a huge effect in computer science.
Yeah, we wondering whether actually this does smell a little bit like a SAT problem. But again, we haven't seen how to map it on precisely.
It's so interesting, because when you were talking about the annealing kind of thing, I mean, where you drop the temperature or raise the temperature, that's a whole area now in computer science called simulated annealing for optimization. So there are a lot of nice interwoven connections here.
Well, there's a lot of threads in this one.
Have you given names to this particular system?
You gotta have a sexy name. You're not gonna get published. So I thought about the spherical Csaaw model, but I think I don't like this name. But the truth is, it's what it reflects. I thought about calling it the stigmergy model or the stigmergy. I don't really like that so much. But if you have a suggestion, let me know and I'll give you an acknowledgement.
Are there any other questions? If not, let's give Bob a round of applause. Thank you.